Hello everyone, my name is Louisa Seelbach. I'm a PhD student from University of Siegen, and my talk will be on a collection of Fringe subtrees in random binary trees, which was joint work with Stephan Wagner from Stellenbosch University, respectively Uppsala Universität. Okay, so first let's start with a small example. Let's say we have some data which might be from a library consisting of books, and those books might have several authors. And let's say this data is given as a tree, and now we want to compress this tree such that we will still be able to recover the original tree back from the compressed representation. Then there's a well-known compression algorithm for trees, which consists in computing the so-called minimal DAG of the tree, where DAG stands for Directed Acyclic Graph. And compression by minimal DAGs has found various applications in several areas of computer science, for example in compiler construction and in XML compression and querying. And the minimal DAG of a tree can be computed in linear time and is obtained by merging root nodes of identical fringe subtrees of the tree, where a fringe subtree of a tree consists of a node together with all its descendants. So here on the left, we see the minimal DAG corresponding to this tree from the top. And here I've highlighted all the nodes with the same color, which are merged in the minimal DAG. For example, we find that there are two red nodes labeled author, and their corresponding fringe subtrees consists of the author node together with their child nodes, first name, middle name, and last name. And those fringe subtrees occur twice, and thus they are merged in the minimal DAG. So compression by DAGs has been analyzed before, and in our paper we were able to obtain some new average case results with respect to DAG compression. And furthermore, we focused on another aspect of DAG compression, namely on the question how much can we profit from unorderedness. So if we look at our tree, then we find that some fringe subtrees are equivalent as unordered trees, namely the fringe subtrees rooted in the nodes labeled book. And now for some applications, it might be sufficient to be able to recover an unordered representation of the original tree back from the compressed representation. For example, there are XML documents for which the corresponding XML document trees are unordered trees. So if this is the case, if we are only interested in an unordered representation of the original tree, then we can compute the so-called unordered minimal DAG of a tree, which is then obtained by merging root nodes of fringe subtrees which are identical as unordered trees. So in our example, we can then merge the two nodes labeled book as well, and thus the unordered minimal DAG of our example tree is smaller than the ordered minimal DAG. And the question we now tried to investigate in our paper was how much better can compression by unordered minimal DAGs be compared to compression by ordered minimal DAGs. So in order to tackle this question, we started off with unlabeled binary trees. So we considered rooted ordered trees such that each node has either exactly 2 or 0 descendants. So this would be a binary tree, for example. And as I already said, a fringe subtree of a tree consists of a node and all its descendants. So this blue subtree here is a fringe subtree. And moreover, the minimal ordered DAG of a tree will be denoted by d of t and is the graph obtained by merging root nodes of identical fringe subtrees. So this is the minimal ordered DAG corresponding to this binary tree. And what's important for us is that the size of the ordered minimal DAG equals the number of distinct fringe subtrees occurring in a tree. So here I've highlighted the nodes with the same color, which are merged in the minimal DAG. And we find that the number of colors I've used in the minimal ordered DAG equals the number of distinct fringe subtrees occurring in a tree, respectively the size of the minimal ordered DAG. Okay, furthermore, we call two trees isomorphic when they are identical as unordered trees. So all those 3 fringe subtrees are isomorphic as they correspond to the same unordered tree. and the minimal unordered DAG of a tree will be denoted by the U of t and is the graph obtained by merging the root nodes of isomorphic fringe subtrees of the tree. So in particular, in our example, we can now merge those 3 red nodes as well, as they are root nodes of isomorphic fringe subtrees. And again, what's important for us is that the size of the unordered minimal DAG of a tree equals the number of non-isomorphic fringe subtrees occurring in a tree. So here I've again highlighted all the nodes which are merged with the same color, and the number of colors I've used now corresponds to the size of the unordered minimal DAG, respectively the number of non-isomorphic fringe subtrees occurring in a tree. So compression by ordered and unordered DAGs has been analyzed before. So first let's start with some previous results and some preliminary observations. So an easy observation is that there are families of trees Tn such that the size of the tree Tn is linear in n, and the size of both the ordered and the unordered DAG is linear in n as well. So an example for such a family of trees would be the family of left degenerate binary trees, for example, which is depicted here on the left, together with the corresponding minimal DAG. And in particular, we find that in this case, the ordered and the unordered minimal DAG are identical and are linear in the size of the tree. And moreover, another easy observation is that there are families of trees Tn, such that the size of the tree Tn is linear in n, and both sizes of ordered and unordered minimal DAG are logarithmic in n, so ordered and unordered minimal DAGs can be exponentially smaller than the size of the tree. An example for such a family of trees would be the family of complete binary trees, for example, which is depicted here on the left, together with the minimal DAG. And in this case, we find again that the ordered and unordered minimal DAGs are identical in this case and exponentially smaller than the tree itself. But moreover, there are also examples where ordered and unordered minimal DAGs aren't equivalent. And in particular, there's a theorem by Markus Lorey, Sebastian Manet, and Carl Philipp Reh from 2016, which states that there is a family of binary trees such that the size of the binary Tn is linear in n, and the size of the ordered DAG of Tn is linear in n as well, but the size of the unordered minimal DAG is logarithmic in n, so exponentially smaller than both the size of the ordered DAG and the tree. So those are the worst case results with respect to this topic. And in our paper, we asked what about the average case? And in order to investigate the average case, we need something like a probability distribution. So a very natural probability distribution is the uniform probability distribution on a set of binary trees of size n. So with Tn, we denote the set of binary trees of size n, and we measure the size of a binary tree as its number of leaves. And then it is well known that the number of binary trees of size n equals the n minus first Catalan number. And then the uniform probability distribution assigns a probability to a tree of size n, namely it assigns the probability 1 over the n minus first Catalan number to each binary tree of size n. So in particular, every binary tree of size n gets the same probability. And next we define some random variables. So with Fn, we denote the random number of distinct fringe subtrees in a uniformly random binary tree of size n. And by our previous considerations, we find that Fn equals the size of the ordered minimal DAG of a uniformly random binary tree. And moreover, with Gn, we denote the random number of non-isomorphic fringe subtrees in a uniformly random binary tree of size n. And again, by our previous considerations, we find that Gn equals the size of the unordered minimal DAG of a uniformly random binary tree of size n. Okay, so the number Fn has been analyzed before. There's a theorem by Flageolet, Sipala, and Stayat from 1990, which states that the number Fn of distinct fringe subtrees in a uniformly random ordered binary tree of size n satisfies this asymptotic estimate in expectation. So the expectation of Fn grows asymptotically as n over square root of log n times this constant. And in our paper, we were able to reprove this theorem with a different proof technique. And also we were able to show the following. So we proved that the number Fn also satisfies the same asymptotic estimate, but with high probability. So Fn asymptotically grows as n over square root of log n times this constant with high probability. Furthermore, we were also able to obtain a first result with respect to the number Gn of non-isomorphic fringe subtrees in a uniformly random binary tree of size n, namely Gn asymptotically grows as n over square root of log n as well, both in expectation and with high probability. So the probability that Gn lies somewhere within this range tends to 1 as n goes to infinity. And furthermore, we provide bounds on the constant in front of the term n over square root of log n. Namely, we provide an upper bound 1.077 and the lower bound 1.059, where in our paper we have computed some more digits with respect to these upper and lower bounds. So in particular, we find that both Fn and Gn are in theta of n over square root log n, both in expectation and with high probability. So that means that the sizes of the ordered and unordered minimal DAG of a uniformly random binary tree of size n are in theta of n over square root of log n, and only the leading constant in front of the main term n over square root log n changes slightly. So furthermore, we investigated another kind of random binary trees, namely so-called random binary search trees. And the binary search tree model randomly generates a binary tree as follows. So if we want to generate a binary tree of size n, so that is with n leaves, then we start with a root labeled with n, and then we choose a pair of integers I and n minus I uniformly at random from the set. And this pair of integers I and n minus I then tells us how the n leaves of the tree we want to generate are distributed to the left and to the right subtree. So the left subtree will then be of size I, and the right subtree will then be of size n minus I. So we attach a new left and a new right child node to the root, label them with I and n minus I, and then we repeat the process. So again, we choose a pair of integers k and I minus k uniformly at random from all these possible pairs of integers, and then the next left subtree will be of size k and the next right subtree will be of size I minus k, and so on. And the process then stops at nodes labeled with 1, and in the last step we leave out the labels of the nodes. So this then yields a probability distribution on a set of binary trees of size n, and in particular the probability of a binary tree T can be written as this product. So it is a product over all nodes of the tree such that the size of the fringe subtree rooted at that node is greater than 1, and then we multiply all these fractions, which correspond to the uniform probability distributions on the set of pairs of integers, which tell us how the nodes are distributed to the left and to the right again at the subtree. Okay, so next we define some random variables again. So with Hn, we denote the random number of distinct fringe subtrees in a random binary search tree of size n. And by our previous considerations, we find that Hn equals the size of the ordered minimal DAG of a random binary search tree. And in a similar way, we define Jn as the number of non-isomorphic fringe subtrees in a random binary search tree of size n, and find that Jn equals the size of the unordered minimal DAG of a random binary search tree of size n. So in this case, again, the number Hn of distinct fringe subtrees has been analyzed before. So there's a theorem by Flageolet, Gordon, and Martinez from 1997, which tells us that the number of distinct fringe subtrees in a random binary search tree of size n satisfies this asymptotic estimate in expectation. So the expectation of Hn is upper bounded by n over log n times this constant. And this result was improved by Devroy in 1998, where he proved a corresponding lower bound. So he showed that the expectation of Hn is in theta of n over log n by reproving the upper bound and by showing a corresponding lower bound. Okay, the constant in front of the lower bound has been improved recently in 2018, slightly. And in our paper, we are able to show that the number Hn of distinct fringe subtrees in a random binary search tree of size n satisfies this asymptotic estimate not only in expectation, but also with high probability. And in particular, we are able to significantly improve the lower bound by providing a constant closer to the upper bound. And finally, we were also able to obtain a first result with respect to the number Jn of non-isomorphic fringe subtrees in a random binary search tree, namely Jn satisfies this asymptotic estimate, so it is in theta of n over log n, both in expectation and with high probability. And moreover, we were able to bound the constant in front of the main term n over log n. So this constant is upper bounded by 1.82 and lower bounded by 1.57, where we provide some more digits with respect to these bounds in our paper. And so altogether, we thus find that both Hn and Jn are in theta of n over log n, both in expectation and with high probability. So the sizes of the ordered and unordered DAG of a random binary search tree of size n are in theta of n over log n. And now if we recall the sizes of the ordered and unordered DAG of a uniformly random binary tree, then we find that the corresponding bound was theta of n over square root of log n. So in random binary search trees, the DAG sizes are smaller in average and with high probability than in uniformly random binary trees. So as future research, we plan to transfer our results to plain trees and to node-labeled trees and to simply generated families of trees, which were introduced by Mir and Moon in 1978 and which provide a more general model for random trees. And this is the end of my talk. Thank you for your attention.
Very much.
Actually, I planned to give the talk in person, but I wasn't able to share my slides, so we had to go back to the pre-recorded talk. But I'll be happy to answer some questions.
So thank you very much, Louisa. The thing I guess that we have only time for a very short question. If there's someone who wants to ask a question. Does anyone want to ask a question? Arnaldo, perhaps?
I have a small question, please. In the context of ordered binary trees, there is the exact value of flageolet and Cipala and Steyart, and what is its approximation according in front of your value for unordered binary trees, please?
For the unordered case, we have this upper and lower bounds on the constant. Yeah. And the approximation is 2 times the square root of the logarithm of b, where b is the asymptotic growth of the Wedderburn-Etherington numbers, which tell us the asymptotic growth of the unordered trees, over the square root of p. And the lower bound on this constant is similar, except that we have some constant gamma, which is from a theorem, a central limit theorem on the number of automorphisms of a uniformly random binary tree.
Okay, thank you, very nice. Thank you.